Hello everyone and welcome back to the recursion series. So this is the third problem that we are solving as part of this series. The objective of the first two problems was to cement your basic understanding of recursion, and here on we'll try to strengthen the thought process behind solving a recursive problem. So before moving on to the question, I would like to add one more thing that we have already discussed how important it is to practice some questions on your own. But the thing is that please use some good platform for practicing like HackerRank, Leetcode or Codeforces. Why I'm saying that it is because the test cases on these platforms are very strong. Because if you're practicing on a platform that has very weak test cases, then there's no point, because even if your code is not absolutely correct, the test cases might not be able to identify the fault. So if you are practicing on these platforms, the test cases are good enough to identify the small mistakes, and you'll be able to see that what you were doing wrong and improve it. So with that being said, let's dive into a problem. So I'll not read the complete statement, but I'll quickly explain what the problem says. So we are given an array of numbers, and let's say the array is 1 comma 5 comma 2, and there are two players who take turns alternatively, and in each turn the player has to pick one number either from the start or from the end. So player 1 starts the game, the player has to pick a number from the start or the end. Then alternatively player 2 will take a turn in the next round, and from the remaining array player 2 has to pick from start or end. It is given that both the players play optimally. So if both the players are playing optimally, we have to return, is there any scenario that both the players are playing optimally, still the player 1 wins? If there is such scenario that player 1 wins, then we have to return true. If there's no such if there's no way that both the players play optimally and still player 1 wins, then we have to return false. And the condition for winning is that every time the player picks a number, that number gets added into their score. So if from 1 comma 5 comma 2 player 1 picks 1, then the remaining array is 5 comma 2, and the score of player 1 is has become 1. And if player picks 2, then the remaining array is 1 comma 5, and the score for player 1 has become 2. Now in the next round, player 2 will be picking up from the remaining array, and whatever number player 2 picks will be added to the score of player 2. Now a very naive thought that might come to our mind is that why can't we use seems like to be a question that can be solved by greedy approach. At every chance, if player 1 is picking the greatest number possible, so every time player has two alternatives, and if the player picks the alternative which is like the best alternative at this stage, why wouldn't that approach work? So let's see, what's the biggest pitfall of greedy approach. The pitfall is that we need to keep in mind that the step we are taking will lead us to a local minima maxima, or will it lead us to a global minima maxima? Because what we want is a global maxima or global minima, and when we are using greedy approach, there's a high chance that we are tending towards a local minima and maxima, and we think that it is the global peak, but it is actually not the global peak or the global valley, and we get stuck there. And if our strategy is not leading us towards the global minima or the global maxima, depending on what we're trying to optimize, then greedy approach is not the correct approach. So let's take an example and see how greedy approach won't work here. So we are given this example, and we can use the same example. So we are given 1 comma 5 comma. Now if the player picks the current highest element, so player 1 has either the option to pick 1 or option to pick 7, and we are saying that the player picks 7 because this is higher. So the remaining array would be 1 comma 5 comma 233. Now since both the players are playing optimally, player 2 in its turn will now pick up 233, and there's no way, if even if now player 1 picks everything which is left, which is not possible, player 2 will get another chance to pick, still player 1 cannot beat the score of 233. And on the other hand, if player 1 wouldn't have picked 7, and instead player 1 would have picked 1, so the score of player 1 would be 1, but the remaining array would have been 5 comma 233 comma 7, and player 2 now does not have an option. The player cannot pick 233, like whatever be the case, the player cannot pick 233, so the second player has to either pick 5 or pick 7. And in any case, in the next turn, player 1 will get a chance, and player 1 will obviously pick 233, because 233 will be remaining. Either will be 233 comma 7 will be remaining, or 5 comma 233 will be remaining, and player 1 will win. So playing the optimal strategy here is not the greedy strategy, because greedy strategy will only give us a good score locally in that stage, but that strategy might not lead us to the global maximum. Now let's see how this question can be solved recursively, or why do we even want to solve this problem recursively. So let's take the same example. We are given an array 1 comma 5 comma 233 comma 7. Now here player 1 has two options. Either player 1 can pick 1 or player 1 can pick 7. But now what does player 1 say? That it is really difficult for me to look into the future and decide that what would be the optimal strategy. What if I delegate my task to the remaining array, in the sense that for the remaining array, what is the maximum possible I can get? And if I have my answer for the remaining array, I can use that answer to calculate that what would be the most optimum strategy at this point. So if player 1 says that I pick 1, and the remaining array will be 5 comma 233 comma 7, and if player 1 picks 7, then the remaining array would be 1 comma 5 comma 233. Now player 1 says that I will not decide which number I am going to pick right away. I am going to delegate the same task to the remaining array, and whatever maximum possible I can get in both the cases, I will add my current score to that maximum possible. And out of that, whatever is the maximum is obviously going to be the best score I can get, because I have seen in the future that what could be the best possible thing. I have taken that, and based on the score I'm getting for my sub problem, I'm just adding my current number and seeing that what would be the best possible strategy at my current stage. So what we can see here is that for solving this complete problem, we have delegated the task to a smaller sub problem, and based on this smaller sub problem, we'll be deciding the answer for our problem. If we want to write the recursion relation for this particular scenario, let's assume that there are two variables I comma j, which represents that what is the array I'm considering right now. So I'm saying that f of I comma j will basically be equal to max of, so I first delegate my problem to a smaller subtask, and I add the current score. And the second option is I delegate it to the other subproblem, so what I have done, I have delegated my task to a smaller subproblem and added this current number and the other subproblem, and based on the answer from these two subproblems, I am finding the answer for my current problem. So that is how, based on recursion, I am able to solve the current problem. Now the most important thing is that since both player 1 and player 2 are playing optimally, the strategy followed by player 2 will be exactly same as followed by player 1. So player 2 will also, whenever it is turn for player 2, what the player 2 will do is that it will delegate its task to a subtask, and whatever the maximum possible player 2 can get for those subtasks, based on that player 2 will decide the optimum current step. And because player 2 is obviously also trying to maximize its score, so we have done this, let's try to draw a recursion tree for a smaller let's try to draw a recursion tree for an example problem. So we know that I is going to be 0 and j is going to be 3 for the above example initially, and it is player 1's turn. What player 1 will do is delegate the subtask to I equal to 0 and j equal to 2, or what it will do is that I equal to 1 and j equal to 3. Now this stage is basically player 2's turn. Now similarly, player 2 will delegate this task to I equal to 0 and j equal to 1, or I equal to 1 and j equal to 2. And player 2 here will delegate the task to I equal to 2, j equal to 3, or I equal to 1, j equal to 2. This stage is basically player 1's turn. Now again player 1 will basically delegate this task to I equal to 0, j equal to 0, I equal to 1, j equal to 1. Similarly here, and similarly here. This will drop to player 2, and player 2 will again call further for say I equal to 1, j equal to 0, or I equal to 1, j equal to 0 again. Yeah, so both the cases will be called because j minus 1 and I minus 1. Now you can see that this could be the base case. This is not a valid case. We have traversed the complete array, and this is not a valid case because the end of the window is before the start of the window. So this, assuming this as the base case, we can simply return the score to be 0, 0 for both the players, because this is the base case, no one can pick anything. Now we have hit the base case. Now we'll start traversing above in our tree, and each player will keep on returning the answer based on the answer of the sub problem. Now if we want to analyze the time complexity of this complete tree, we see that if I is equal, we start from I equal to 0 and j will be equal to the size of the nums array. So what could be the total height? We see that either we do I plus plus or j minus minus in each step, and what are the total number of operations that we can do? That is going to be the total size of the nums array, and let's assume the size of the nums array is n. So the total height of this tree is going to be n, and at every stage we are delegating our task to two smaller subproblems. So there are two calls at every stage. So at first there is going to be one node, at second stage 2 node, at third stage they're going to be 2 raised to power 2, then again 2 raised to power 3, so on and so forth. So we know that the sum of this GP will come out to be approximately equal to 2 raised to power n. So there are total 2 raised to power, close to 2 raised to power n nodes in our tree. So the time complexity for our approach will be big O of 2 raised to power n. Now there's one more important thing that we need to identify. Like we in our previous videos we discussed that one of the base problems a lot of recursive approach suffer is that we are calculating answer for same sub problem again and again, and this problem we can see here as well. So if you see one example being that I equal to 1 and j equal to 2 is being calculated twice. Similarly, if we would have got a bigger example, and if we would have drawn the complete tree, we would have seen that a lot of times the same sub problem would have been calculated again and again. So in what comes handy when we are calculating the same sub problem again and again is DP. So we could have stored this the answer for this particular sub problem somewhere and not calculated it, but that is something we'll learn in another series. So right now we'll not optimize it and follow our recursive approach to solve this problem. Now that we have discussed the intuition why we picked up recursion, and we have discussed our approach, and as well as drawn given the recursive relation, the recurrence relation, we have drawn the recursive tree, and we have identified the time complexity. Let's try and actually code the solution, and as I'll code the solution, I'll keep explaining the intuition I'm following. So one thing that we often notice while writing recursive solution is that a lot of times we'll be using a helper function. We might not be able to use the actual function for recursion. That is because for making our recursive calls, we need some extra parameters, and these extra parameters are not part of the current function, as you can see. So we might need some extra parameters, and for that we'll make a helper function. In this particular case, we want to keep the bounds of the window or the remaining array that we have. So as we explained in the solution, we have something known as I and j, which are trying to give that what is the remaining part in the array helper function. Now why I am keeping the return type as int comma int, because for every sub problem what I am trying to do is that I'm trying to return the maximum possible score for both the players, considering both the players are playing optimally. So pair is a good data structure in STL that we use to return a combination of two numbers. In case if you are using, I'm not sure what is the perfect container in Java. In Python you can simply return two values, but in Java you might have to make a custom object or use some advanced container, and in C++ you can use a pair. So let's keep the name of the helper function as maximize score. Then we obviously have nums array, and as we discussed we have int I, int j, and we need another helper parameter int turn. Basically int turn will tell us that whether it is player 1's turn or player 2 has to take a turn. So let's first make two if condition, like if it is the turn for player 1, else it is player 2's turn. So let's say that we do nothing, so we simply delegate the task to a smaller subproblem, and we have to change turn. So we'll give turn to player 2 by changing our turn variable. Now what we have done is we just assume that our function works. We have delegated our task to a smaller subproblem, and what our intuition says is that we don't have to worry how it works for the smaller subproblem. We know that it works for a smaller subproblem. So now what we can be sure about is that we have got the correct answers for our subproblems. Now using these correct answer for our subproblems, we have to calculate the current answer. So what would be the current answer? So if I'm assuming that the first element in the pair will be the maximum possible score of player 1, and otherwise it will be player 2. So if it is the maximum, so in this case what player 1 will do, it has got the answer for the smallest subproblem. Now using that answer it will try to maximize its score. So if choosing I gives a bigger score than choosing j, in that case it makes sense to pick up I. So what we will return from here is a pair which is simply saying that we picked the ith element, and the score for second player wouldn't be affected here because it's just first player picking, and the score of first player will only be affected. But in case the picking up jth element made more sense, so in that case we'll simply return saying that the first player picked up jth element, and we will return the score of second player as it is. Sorry, I added that in the wrong else statement. So that else statement is going to handle the cases when it is the turn of second player. So yeah. Now similarly for second player is also going to follow the same procedure. So what second player is going to do is, the only difference is that in the next sub problem it will delegate the turn to first player. So again the second player has called the answer for the smaller sub problems. Now what second player will do is that it will check whether picking the ith element or jth element, whichever element was beneficial. So here we will not change the score of player 1. If picking up ith element was beneficial, so second player will pick that element. If picking jth element was beneficial, second player will pick that element, and again we will not change the score of first because it is second chance. Now we have written the intuition. So this is the first step of the intuition, where we just delegate our task to a smaller sub problem, assume the answer is correct, and take our current step. What is the base case? As we discussed in the tree, that if I becomes greater than j, then obviously this is not a valid array. So what we need to do is return a score of 0, 0, because no player will be able to pick anything, and if no player is able to pick anything, then the correct score is 0, 0. So one of the biggest issue while doing this is that people make this helper function, but they forget to call this helper function from their main function. So don't do that. So we have the answer, and we will call max my score with the correct parameters. Nums I will be 0. The first value for j will be basically the last index, and the first turn will be player 1 turn. Now I have got the maximum possible score for player 1 and player 2, considering both play optimally. Now the only thing I need to return is check that if this score is greater than equal to the score for second player. So I have got the maximum possible scores, and I am considered both play optimally, and now I am trying to find out that if both the plays optimally, was there a way that the first player could have got more score than the second player. So this is the complete solution. I think we should try and run it. So yeah, we were able to run this solution, and I think it gave us the correct answer. Now one thing which we need to consider is that our complexity, as we calculated, was 2 raised to power n. So the question was generous enough that the size of the nums array was 20. So 2 raised to power 20 was within the limit that we could have actually calculated. If the operations would have become a lot more, if this n value would have been a lot bigger, we wouldn't have been able to run a program with time complexity 2 raised to power n within a given range of like 1 second or 2 second computation time. So due to the constraints, we were able to solve it recursively without applying any optimization. But if this constraint was greater, we would have to apply some kind of an optimization. So I guess that's it, guys. I hope that you understood the thought process, and you were able to appreciate how we applied our basic intuition here as well, our two-step intuition. If some doubts are still remaining, please do mention in the comment section. I'll try to solve all the doubts. So I guess that's it. Goodbye, guys. Take care and keep learning.